In this tutorial, we will be looking at how to design a bias network for an RF transistor and also at how to measure its S parameters at the specific bias levels that we've designed our bias network for. The first thing that we need to do when designing a bias network for a transistor is plotting the IV curves for this transistor so that we can work out the essential parameters that we need for our design. So first of all, let's right-click on Circuit Schematics, open a new schematic, and we'll call it IV curves. And then we need to put our transistor in the schematic. For our design, we are choosing a transistor which is produced by Infineon, and its model number is BFP405. Now we can go on to the Elements tab and then scroll down to the Libraries and then click on the plus to expand, and then expand again on AWR website and select Parts by Vendor. Then we can scroll down until we get to Infineon and we can select the nonlinear models and GBJT. Now you can see that we've got a number of parts which are listed under the nonlinear models for GBJTs, and the one that we're interested in is the BFP405. You can also see that as you hover over with the mouse on any of these transistors, a brief description of their features and application is also shown. So we'll just click on BFP405 and then we'll drag it onto the schematic, keeping the left button of the mouse pressed, and then we release it and click to place it. Let's move the name out of the way. And you can see that we've got a simple BJT here with a collector, base and emitter terminal. The design specifications for our amplifier are that we want to have a collector to emitter voltage, VCE, equal to 2 volts and a collector current of 2 milliamps. A configuration that is often used for RF amplifiers is one which has the emitter terminal of the BJT grounded or the source terminal of the FET grounded, and this is to avoid the feedback that can originate from having any elements between the emitter terminal and the ground, which can reduce gain. So let's just get ourselves a ground terminal by pressing Ctrl G and connect it to our emitter. Now, as you know, the BJT is nothing but a current controlled current source. So you basically have a current which flows between the collector and the emitter terminals, which is regulated by the current which is injected into the base. So the current into the base is your control current, and this is then amplified to create a collector current which is then used for your load. The ratio between the collector current and the base current is usually defined as beta, which is the current gain of the transistor. So what we want to do is inject different levels of bias current into the base, and then we want to see the variation of the collector current across a range of voltages. What we will get is a set of curves which will represent IC versus VCE, so the collector current versus the collector voltage, and each one of these curves will be relative to a specific bias current which we inject into the base. So what we want to do is have a current generator for the base which generates specific bias currents, and then we want to be able to sweep the voltage of the collector so that we can see the variation of the collector current across voltage range. And we have an element in Microwave Office that can do just that. So let's press Ctrl L, and in the search box let's type IV curve. And you can see that we've got two elements displayed. The first one, IV curve I, is a current-driven curve tracer. And this is what we need, because we said that our transistor, our BJT, is a current-controlled current source. So the current-driven curve tracer is what we need, because that's what drives our transistor. In the case of a FET, however, we would have a voltage at the gate which biases the transistor and gives us different levels of current. So we will need to use a different curve tracer, which is the IV curve, and this allows you to have bias voltages for your gates and then to sweep the voltage across a specific range for your drain and then to see the drain current that results from that. But for us and for BJTs, we want an IV curve I element, and so we double click on it and then we place it on the schematic like so. So as you can see, there are two quantities that are varied here. The one at the bottom, which is I step, is the one that represents the bias current we are injecting into the base. So we'll have a set of bias currents, each of which will create an IC versus VCE plot. So let's connect the step terminal to our base. And then, of course, as we said, we're going to be sweeping the collector voltage and see how the collector current varies across a range of collector voltages. So we connect the sweep terminal to our collector terminal of the transistor. So let's move this out of the way a little bit so we can see it a little better, and click on View All. We inject a current into the base which gets amplified by quite a large factor of beta and turns into this collector current. Now the base current tends to be a lot smaller than the collector current. So as a unit, it's much better to use microamps rather than milliamps for it. And so this is what we'll do. We'll change the unit for the current for now to microamps in the project options. This is why I haven't just gone to project options yet. I was waiting to put this together so I could justify the reason for changing the current units to microamps. So to change this, we need to go back to the project tab and then double click on project options, and on global units we can set our conductance to millisiemens as usual, inductance stays into nanohenries, capacitance will shift down to picofarads, and current to microamps, and then click on OK. At the moment we are not carrying out any measurement at the frequency of operation of our amplifier, which will eventually be 1.9 GHz, so we don't need to worry about the frequency in the project options. We're just working with DC voltages and currents to work out how to bias our transistor. In terms of the voltage sweep at the collector terminal, this transistor can take a maximum voltage of 4.5 volts. So sweeping up to 4 volts is more than enough for us. And also we want to achieve ultimately a VCE of 2 volts as per our design specifications, and so going up to 4 volts is more than enough. However, we will refine the step and we'll set it to 0.1 volts. In terms of the current, obviously we want a current which is much lower than the ones shown at the moment, more of the order of microamps or tens of microamps. So we can start with 0 microamps and we can go up to 40 microamps, and we can step in steps of 4 microamps. Of course, if you don't know the data of the transistor, this may be a bit of a trial and error process. Usually from the data sheet you'll be able to gauge what the beta of the transistor is going to be, how much is going to amplify your base current. So if you have a specification for your collector current, then you'll know more or less what range of base currents you want to go through. But all the same, we can just try this range, and if it's not enough, we can always refine it or change it if we want to make things more visible or zoom in a particular bias region. So the measurement is set up in our schematic now, and as usual we'll create a graph to display the results. So let's right click on graphs, select new graph. We'll also call it IV curves, and it's a rectangular graph, as you may imagine. So we'll have the collector current on the y-axis, the collector voltage on the x-axis, and then you will have more than one curve. Each curve, each xy curve, will be relative to a specific bias current which we're injecting through the base. So let's right click on the graph to add a measurement. We'll have to go to nonlinear measurements, and then we'll have to choose current, because that's what we want to display as a variable on the y-axis, as a dependent variable. And then we'll choose IV curve as the measurement that we want to display. As you can see from the description, this will give you the current at the swept terminal. Our swept terminal is the collector, so this will give you the collector current. Finally, let's select the data source name as IV curves and click on apply, and then OK. Then simulate. Now you can see that you've got a set of curves, each of which represents the collector current versus the collector voltage, or the collector to emitter voltage, since the emitter is grounded. And you can see that each curve is relative to a specific bias current that we're injecting through the base. And you can see which one it is by just getting to the end of the curve, looking at this little number here, this marker here, and then looking at the legend. Now, talking about that little number, it is not very legible, is it? So what we can do is right-click on the chart, and then go on to Properties, and go on to the Fonts tab, and then we can select Markers, and we can change the color of the font to red, and then you can select the size to be something like 20, click on OK, and then Apply, and OK again. And you can see now that the font makes things more legible, and so you can see which curve corresponds to which number, and then read it off the legend quite easily. Now we want a VCE of 2 volts, and then we want a collector current of about 2 milliamps. So as I go up this vertical line from the 2 volts point, I can see that the closest point to 2 milliamps is this one here. So I can just press Ctrl M and add a marker right here. And then I can move the marker slightly just to position myself right on 2 volts, as close as I can to it. And you can see that I can get to my specifications within a certain degree of accuracy. I've got a 2 volts VCE voltage now, and a current of about 2000 microamps, which is 2 milliamps. So what base current gave me this curve? I just have to follow the curve all the way up to the top, where I can find a marker which uniquely identifies the bias level that was used for this particular curve. So I've got P7, and P7 corresponds to a base current of 24 microamps. So I need to have a 24 microamp base current to get a collector current of 2 milliamps when the collector to emitter voltage is 2 volts. The other thing that I can work out from this data that I've got here is the beta of the transistor, the current gain, which is nothing but the ratio of the collector current and the base current. And in this case, if you carry out this calculation, you can see that beta turns out to be roughly 86. And of course it's adimensional because it's the ratio of two quantities with the same units. So let's go back to our schematic now, and we can recap briefly. We've grounded our emitter here, so we've chosen a common emitter configuration for our transistor, and we worked out that we need to have a base current of 24 microamps to be able to obtain a collector current of 2 milliamps when the collector to emitter voltage is 2 volts. Now that this is done, we can go back to project options, and we can change the units of the current back to milliamps, because what we will be dealing with mostly will be currents of the order of milliamps, and click on OK. Now we can forget about our IV characteristics and our IV curves and move on to designing the bias network for the transistor. So let's just right click on Circuit Schematics, open a new schematic, and we'll call it DC bias. And then of course again the first thing we need to put in is our transistor. Instead of going back to the Elements tab and fetching it from there, we can just go back to our previous schematic, click on the transistor, press Ctrl C, go back to our schematic, press Ctrl V, and here we have it. So you can copy things across between one schematic and another. Then we'll insert a ground reference on the emitter lead, and then we need to work out a way to generate a voltage of 2 volts across the collector to emitter and a current of 24 microamps which goes into the base. There are a number of biasing arrangements that can be worked out. Some of them are completely passive, so they only use passive elements, and some others use active elements. We will be looking at different, more complex bias arrangements in the future, but for now we'll just keep it simple, and we'll just use a bias arrangement with 2 resistors. So let's get ourselves a resistor by pressing Ctrl L and typing in RES, and then we'll place it in series with the collector. And then let's copy this resistor by pressing Ctrl C and Ctrl V, and we'll rotate it, and we'll use it as a base resistor. We'll talk a little bit about why this arrangement is chosen and work out the values of the resistors in a second, but first of all we have to get ourselves a DC power supply. Because we want to obtain a collector to emitter voltage of 2 volts, a power supply will have to be somewhat higher than that. Usually if you choose it to be about twice that, you get good stability for the transistor. This is another topic which we'll be talking about later on, but in our case we'll choose it to be something like 3 volts, which can be easily achieved with batteries. So I'll just press Ctrl L and fetch a DC voltage source, and then place it on the schematic, connect it to ground on one side, and then to my collector terminal through resistor R1 on the other side, and we'll give it a value of 3 volts. Now we can change the ID of our collector resistor to make it more recognizable, and we'll call it RC, and then we'll change the ID of our base resistor to RB, just to avoid confusion. The good thing about this arrangement is that it provides some sort of feedback within the DC bias network. Feedback usually is not great for an amplifier in terms of its RF performance, but when it comes to DC it's actually quite good. And I'll explain to you why in a very simple way. There is a number of reasons, but this is one of the main ones. Suppose that the current of your transistor changes with temperature. So your transistor at some point starts drawing more and more collector current. So the IC here gets greater and greater. This means that the current through the resistor RC is going to get greater overall, and hence you get a bigger drop across the resistor RC. This means that the voltage at the collector terminal VC is also going to be smaller. And because this voltage is going to be smaller, then the voltage of the base is going to be smaller as well, which translates into a lower base current. So you're lowering the base current, which is biasing your transistor, and because you're lowering that, then your collector current also gets lower. So effectively your collector current can try to increase, but then when it tries to do that, because of the bias arrangement, you end up decreasing the base current, and that has the opposite effect, that of decreasing the collector current. So this provides some sort of feedback loop which allows you some certain stability over temperature, for instance, but also in other respects. So let's move this out of the way a little bit. Let's also change the ID of our power supply to VCC. So we've got our design specifications. We said we want a collector to emitter voltage of 2 volts and a collector current of 2 milliamps. So because the voltage at node C of our transistor has to be 2 volts and the voltage of our power supply is 3 volts, also the current through RC has to be roughly 2 milliamps, we can easily calculate the value of RC. And this turns out to be 500 ohms. You may say, well, why are you saying that the current through RC should be 2 milliamps when it's actually the current between collector and emitter that should be 2 milliamps? Well, the thing is, because we have quite a big beta here, we can just assume that the current through the resistor RC and the current between the collector and emitter, the collector current, are actually more or less the same. And this is because IB is much smaller than IC. This simplifies the calculations, and you will see that it kind of works out pretty well. Now, let's also assume that for this particular technology or transistor, VBE is 0.8 volts, so the base emitter voltage is 0.8 volts. We can then, using KVL, write an equation which tells us that VBE plus the voltage drop across the base resistor plus the voltage drop across the collector resistor is equal to VCC. On this equation we can calculate RB quite easily. Remember that IB, the current through the base, is IC divided by beta, and we can work things out as shown in the equation, and we end up with a base resistance of 50 kilo ohms. So we can insert the values into the schematic and verify them. We said that RC was 500 ohms and that RB was 50 kilo ohms, which is 50,000 ohms. Now, to verify that we have the right DC voltages and currents at all the nodes and across the various elements of a bias network, all we need to do is just right-click on the name of our schematic, and then you can see that you've got an option to add an annotation. So let's just click on that, and then you can choose a number of annotations there. The ones that we will choose will be DCIA, which gives you the DC input current for all elements. So we select that and click Apply. And then DCVAN, which gives you the voltage for all the nodes. Click on Apply and then OK. Now, if we click on Simulate, you can see that we get the voltages and current for every element. And you can see that we've got about 2.01 milliamps. We can say this is close enough to our design goal as a collector current. We have about 1.98 volts at the collector terminal, which makes VCE approximately equal to 2 volts. And hence we really have achieved our design goals. Of course, we can use optimization or tuning to change things slightly, but I think we can be happy with what we have achieved. And you also have to bear in mind that in real life you will have to use preferred values for your resistors, for instance, and they will have a tolerance on them. This is another reason why having some sort of feedback network within your DC bias network is good, because of course you will have some tolerances on each element that you choose, and then having this kind of feedback mechanism may help smooth out some of the effects of the imperfect values of your chosen resistors. A couple of other things to point out here. We had a bias current of about 24 microamps in our IV simulation. We have about 22.6 here, which is not too far off. And you can also see that we've used a value of 0.8 volts as the base emitter voltage for this technology, but this turns out to be slightly higher at about 0.85. Of course, the calculation was approximate, but it led to a decent arrangement. And always remember that you can't choose perfect values for your elements once you put the bias network together in real life. Now, let's get a bit more of an insight into how this bias network works. It is always good to play around with these circuits and familiarize yourself with them and try and understand what's really going on. And the tuner is a great tool to do this. MicroOffice offers you a fantastic tool. So click on the screwdriver icon, and then let's make RC tunable and also RB tunable. And then let's open the tuner. You can see that you can have the tuner in a schematic as well when you're doing a DC simulation. It doesn't have to be related to a graph. So as you can see now, because you've got a specific ID for your resistors, it is much easier to find out which one is which, and that's why I changed the IDs earlier on. So the bias resistor RC, if you decrease its value, you can see that you are letting more current through, of course, and therefore you're getting more current into the collector of the transistor. And the opposite happens if you increase this resistance, and you're letting much less current through. Let's get it back to what it was. And then you can see also that with the base, you can expect that if you decrease the resistor, you will have more current going through the base. And because you have more current going through the base, then you're getting more collector current, because the two are proportional to one another. As you increase the base resistor instead, then you're letting less bias current into the base, and hence you will decrease the collector current. So whereas there is a direct proportionality between the collector resistor RC and the IC current, the current through the collector, there is an inverse proportionality between RB and the current through the collector. So let's just reset to the values we had, and then we'll just close the tuner. So now what we need to do is put this DC bias network together with an RF network, which enables us to use this transistor as an RF amplifier, as a high frequency amplifier. So I've got my bias circuit all worked out. I don't want to particularly have to redraw it all. So what I can do is just either right click on its name and select duplicate schematic, or just drag the schematic onto the circuit schematic heading to create a copy. So I've created a copy, but what I need to do is rename the schematic. So let's just do that, and we'll call it S parameter measurement. And now what we need to do is, of course, insert some measurement ports to measure our S parameters. Now that's easier said than done. The thing is, you've got some ports which have a specific impedance, usually 50 ohms. And this 50 ohm impedance is relatively low compared to the other resistances that are here in the circuit. If I connect a source with a 50 ohm internal impedance here, for instance, then I'm going to load my bias circuit and I'm going to allow current to flow back into my RF source. So that's not very good at all. Same thing if I put a test port here at the collector terminal, then I will load the DC bias network as well, which is also not good. So I need to find a way to isolate the two. Now there is an element which is very obvious and would do the trick, and that's a capacitor. If you put a capacitor between your RF source and your DC network, of course at DC the capacitor is an open circuit, so the DC currents can't flow through it, but the RF currents can go through quite easily. So let's get ourselves a couple of capacitors by pressing Ctrl L and then typing in cap, and then I can use Ctrl C and Ctrl V to have a second cap and my output. And I'll also make a little bit of space here so as to avoid things being too crammed. So my input for my transistor will be my base, and my output will be my collector terminal. And as I said, I need to be able to isolate the DC network from the RF network. Here I will have a source with an internal impedance of 50 ohm, which is represented by a port. So let's get ourselves a port by using Ctrl P, and then we'll connect it right here. So now when I get a DC current here, the current won't be able to go through the capacitor, which is an open circuit at DC, and hence the bias network won't be loaded by the 50 ohm internal resistance of my RF source. Similarly, when I put an output test port on this other side, because the capacitor is an open circuit at DC, the 50 ohm impedance of this port won't be able to load my DC bias circuit either. But what value of capacitor should I choose? This is quite an important issue. So let's open a new schematic and we'll call it DC block capacitor, and then we'll put a capacitor in here connected to a test port, and we'll see what impedance this has on the Smith chart. So let's press Ctrl L and then select a capacitor, connect it to ground on one side, and then get a test port which will connect to the other side to see its impedance on a Smith chart. We'll also make this capacitor tunable over a specific range and select an initial value for it. We can do this by double-clicking on it, selecting, let's say, 10 picofarads as a start, making it tunable, enabling some limits, starting from 10 and getting up to 100 in steps of 1 picofarads. Click on OK. So before we carry on, we need to set a specific frequency, which will be our frequency of operation, because as we know, the impedance of a capacitor is frequency dependent. So let's go to project options and select our frequency to be 1.9 gigahertz, select single point and then apply and OK. Then we'll go to graphs, choose a new graph, it'll be a Smith chart, and we'll call it DC block impedance, and then we can right click on the chart, go on to add a new measurement, and of course we'll want an S11 measurement from our DC blocking capacitor schematic, because this allows us to see the impedance of the Smith chart. Click on apply and then OK. Then simulate. Now we can add a marker on our point to see it a bit better, and we can also change the impedance readout to be denormalized and also in terms of magnitude and angle. So let's right click on the chart, go on to properties and then on to markers, and we choose to have our readout denormalized to 50 ohms and to display it as magnitude and angle. Click on apply and then OK. Now you can see your impedance is about 8.4 ohms. in terms of its magnitude at the frequency of interest. So if you use the value of 10 picofarads, which was the initial value that we set our capacitor to, of course you'd have no problems in terms of the bias circuit being loaded, because DC currents can't go through any capacitor really. So that doesn't matter, that is not the issue. But your microwave or RF frequencies would encounter an impedance of about 8.4 ohms. So you might have some losses through that impedance. And what you ideally want to have is something which at DC is an open circuit and at RF or whatever frequency you're working at is a short circuit. So what can you do? Well, you can increase the value of the capacitance, because by increasing that, seeing that the major contributor to the impedance of a capacitor is its reactance, which is 1 over omega C. By increasing C, you're decreasing this reactance and hence the impedance that's seen by the source. So we can just open the tuner and we can increase the value of the capacitor, and you can see that we get, when we get to about 100 picofarads, we get to a magnitude for our impedance which is about 0.8 ohms. And we are very close to the resistive axis, to the 0 point on the resistive axis of the chart. So ideally that's where you want to be. You want to be on the resistive axis and be at the 0 point. But with a capacitor you can never achieve that. A capacitor alone will always keep you in the bottom half of the Smith chart, and hence the impedance magnitude will never really be 0. So we could put this capacitor value in, we could put 100 picofarads as our DC blocking capacitor, and that would work pretty well. However, when we think about a real capacitor, we have to think about the parasitic elements that come with it. So if we look at the model for a capacitor, you've got some resistive loss, which we will ignore for now, but also we'll have some sort of parasitic inductance in series with the capacitor. And hence we end up having a series LC resonator. You can actually find an element which has got a capacitance value associated with the parasitic inductance value, which makes it resonate at the frequency at which you're working, and then at that frequency your impedance will be exactly 0. So actually having a parasitic inductance as part of your real capacitor is not a bad thing, because it allows you to use this capacitor as a resonator effectively, and hence achieve very low impedance at your frequency of interest, although of course this is quite narrow band. The frequency at which your capacitor and the parasitic inductor associated with its construction resonate is called the self-resonant frequency. So ideally your DC blocking capacitor should be a capacitor whose self-resonant frequency is the frequency at which you're operating. Now let's close the tuner and go back to our DC blocking capacitor schematic and add an actual capacitor, a real one for which we have a model in Microwave Office which will take into account its parasitic elements and not just its capacitance value. We can yet again go to the Elements tab, and then we can pick a different manufacturer. We'll pick Murata, and then we'll expand it, and we'll choose capacitors of course. And then amongst the various types that we've got, we'll look at the high frequency type, and as a size we'll choose 0603. And of course there is a number of capacitors listed under there, and we'll pick one which has got a much lower value than the one that we worked out just by using an ideal capacitor. So we worked out a value of about 100 picofarads for our ideal one, and in this case for our real capacitor we will choose one which has got a value of 20 picofarads. So again you just click on it and then drag it onto the schematic, release it and click to place it. So again we'll get a ground connection to put on one side of it, and also we'll add another port to be able to see its impedance. Now if we go back to our Smith chart, we can right click and add a new measurement. Again from the same schematic, but this time it'll be an S22, which allows us to see the impedance at port 2, which is the impedance of the real capacitor we've just put in. So click on apply and then OK, and then simulate. So let's put a marker in here by pressing Ctrl M and clicking on the pink square, and then we can just move it to one side. So you can see that whereas with an ideal 100 picofarads capacitor we achieved a magnitude for Z of 0.8 roughly, with our 20 picofarads real capacitor, which is going to have some inductance associated with it, we managed to get to 0.1 ohm, which is lower than the one that we achieved with a greater value of capacitance. And that is because, of course, whereas an ideal capacitor cannot go over in terms of the value of its impedance to the other side of the chart, a real capacitor, which has got some inductance associated with it, has got this extra push due to the value of the inductance at a specific frequency, which can take it up to the inductive part of the Smith chart. But of course, the place where you want to be is on the resistive axis of the chart, which is where we are now. And when you're on that axis, it means that your capacitance and your inductance are resonating, thereby giving you the minimum impedance possible. We can also open the tuner again and select our value for our ideal capacitor of 20 picofarads. And you can see how this makes the difference even more noticeable. So you see, you can't really get away from the real implementation of your components. You should always have some kind of real models when you do your design, which allow you to select the values of your components in such a way as not to have surprises when you come to the final implementation. So let's close the tuner and let's go back to our S parameter measurement schematic. So we can either keep the ideal capacitors here and have a value of about 100 picofarads for each of them, or we can just use the capacitors that we got from our library, which have a lower value and give us a better representation of the real element. I actually think that it's better to use real components, and hence I will just go back to my DC block schematic and press Ctrl C and copy this capacitor to my S parameter measurement schematic in place of the one that I've got there at the moment, which is just an ideal one. So I'll put one at the input and one at the output. So now I've managed to put some elements in my schematic which guarantee that the bias network I've designed so carefully for my transistor won't be loaded by the relatively low impedance of my test ports. So the DC can't get out into the RF ports and be loaded by their impedance. However, you don't just want the DC to stay within the bias network and not get out into your RF ports, but you also equally don't want your RF to go back into your power supply. So there are two main routes that you want to block. One is that the DC current would use to get out into your RF ports, which would alter your bias. And the other one is for your RF, your high frequency signals, to flow back into the bias network and up to the power supply, because this would then create a modulation of your DC bias, and it would not just create a bit of a mess with the stability of your DC bias, but also create some considerable losses in your RF performance. So how do we achieve that? If we put an inductor in series with each bias resistor, when the microwaves try to flow back into the bias network, they will encounter an impedance which is very high, because the impedance of the inductor is proportional to frequency, and hence they won't be able to flow back into the power supply. However, the DC currents will see the inductor as a short circuit. So this seems like an arrangement that might work. So let's rejig our schematic a little bit just to make things a little bit easier. So I've just moved the resistor in such a way as to make space for the inductors that I'm going to use. I'll just press Ctrl L and fetch an inductor and put it in series with the resistor RC, and then use Ctrl C and Ctrl V and put another inductor in series with the resistor RB. So let's reconnect RC to the power supply and then connect it through the inductor this time to the collector terminal of my transistor, Then let's connect our B to the collector as well, as we did before, and connect it to the base, but now, yet again, we will connect it by using the inductor in between the base terminal and the base resistor. So what's going to happen here is that when the microwaves come from this port and through the capacitors, they will see a high impedance here, and hence they won't be able to go back in here. And equally, any high frequency signal that's coming in or out of the collector terminal will not really be able to flow up to the power supply, because on the path to it, it will encounter a very high impedance element, our inductor, which will prevent it from reaching the power supply. Now, again, we find ourselves in a situation where we have to pick the right value.